remember about the level. Okay, so following straight on, so we deduced that k times k plus l has to equal l times l plus 1, and so one obvious solution is just k equals l, but there's another one, maybe not quite so obvious, and that is that k equals minus l plus 1. Alright, convince yourself that that solution is a solution. Why would that work? Alright, anyway, so there are two possibilities, okay? Now we can reject the idea that k equals minus into l plus 1 because that means that you would have a power of rho in your f, in your expansion, of this form, right? If that's your k, the smallest term in your expansion. But as rho goes, if that's legitimate, if that's allowed, then as rho goes to 0, then this term here goes to infinity, right? So that's out. So we reject this possibility. So that only leaves one. So k, the smallest term. This is the smallest term in your weighted sum of powers of rho. Right? So that weighted sum, the smallest term, k, is L, just equal to L. So we've made some progress. Okay? Now L, so therefore our f then, we can write in this form. So, weighted sum of powers, and let's see, why this term? We've just shown that k equals L, and smallest value, I guess, smallest value of L is 1. Does that make sense? So when p is nothing, you're just left with rho of 1. So I guess that implies L is 1, smallest value of L. Right. So plug this into your equation. So the equation of the, well, you can't see it, but the previous session. So plus circle was the equation with the differentials of f. Okay. Now do it in general and find the general coefficient. In fact, you'll find a relationship between two coefficients for the coefficient of the rho to this power, p plus l plus 1. And you may ask, well, why concentrate on that particular coefficient? Well, because it's convenient, because it gives you one coefficient in terms of the coefficient where p is one integer, one level down. So you got here the coefficient a p plus 1, that's in this form, p plus 1, in terms of what it is for a p. So if you know what the coefficient for a p is, you can find what the coefficient is for a p plus 1. So it's a kind of, it's a recursion. You've got a recursion relation here. So that means if you know what a naught is, you can find what a1 is. And if you know what a1 is, you can find what a2 is, and so on. Right? Using this recursion relation, which you get by looking, by plugging this into the plus circle formula from the previous session. Okay. So that means that we know these coefficients, and if you know the coefficients, we know what f is, which is what we're after. Okay. So that's all very nice. But there's a problem. Now we've done this kind of analysis before, And the trick we use to solve this problem, and it's the same problem, the trick we use is also the same problem. There's the same trick. Okay, so watch the following. Divide both sides by AP. So this AP comes here underneath, so you get something like this, and bring this term under here to the right hand side, and then let P become large. Well, you'll have these terms become negligible compared to P if P is large, and this term underneath you've got a P squared that will dominate. The other terms forget about. So effectively you've got AP plus 1 divided by AP in the limit becomes effectively just a constant over P. Right? Well, just effectively 1 over P. Now, this converging to the form 1 over P, that's very similar to what happens with the coefficients of the exponential. So if you expand out the exponential function, e to the rho, remember that's what, 1 plus rho squared over 2 factorial plus rho cubed over 3 factorial plus rho to the 4th over 4 factorial, etc. Well, if you expand out, if you put the ratio of let's say the p plus 1th coefficient for exponential divided by the pth coefficient, it too will go like this. It will converge to something like this. So in other words, if with this sort of phenomenon happening, that means that this term here starts with, if it goes on, if p goes to very large, p goes to infinity, let's say, then this expression here behaves like an exponential and blows up, and that's the problem. So we don't want that. Physics hates infinities. So what to do? Well, we did the same trick as before. We put a limit, an upper limit, on the power of your p. So that this weighted sum term has a maximum power of rho. That's what we do. And how can we do that? Well, same trick as before, a couple of chapters back. Here's the trick. This lambda here, let's choose it so that it equals this, some integer p plus L plus 1. Now, can you see what's going to happen then? And we talked about this before, so this is revision. So if you do let lambda equal 1 plus L plus some positive integer, then this term will disappear. Okay, be 0. In which case, a of this coefficient a of p plus 1 will be 0. And then if a of p plus 1 is 0, a of p plus 2 will be 0. And all the coefficients above that will all be 0. And hence this weighted sum is finite. It becomes a finite weighted sum with a lowest power of rho and a highest power of rho. And so this f then is just a polynomial, a weighted sum of powers of rho, where there's a lower limit of the power and an upper limit of the power. Okay. Now, so what does that say? So we're getting restrictions now on the value of lambda, and remember, lambda is our clue, our doorway into finding the values of the energy eigenvalues. Right? So putting restrictions on lambda indirectly puts restrictions on the allowed values of the energy eigenfunctions. Eigenvalues, sorry. All right. So our trick is to let lambda be some integer plus L plus 1. So that means as P keeps rising, eventually that P plus L plus 1 will equal lambda, which is some integer, positive integer, plus L plus 1. And then these three terms cancel with lambda. And so that makes this 0, therefore that's 0. And that solves our blow-up problem. Alright, so let's talk a bit more about what this lambda can be. Because if we can put constraints on lambda, that puts constraints on the energy, the eigenvalues of energy. Alright, so let's see. So we want lambda to be greater than L. It's here. Because what? P's positive, L's positive. So this is all positive, right? We don't want lambda becoming negative, right? If lambda goes negative, then minus lambda is positive, then this whole thing's positive. It can't become 0. So now L's just the angular momentum. So that's non-negative. So L's non-negative. So what's the smallest value we could have for lambda that makes this trick work? Well, P could be 0. That's the smallest, right? Angular momentum, can that be 0? I suppose so. Seems reasonable, right? So the smallest value for lambda then to make this 0 is just 1, and it's an integer, so it could be 2 or a positive integer, or 3 or 4. So let's say, so the lambda then is just the counting numbers. It's just the positive integers. So we can just say lambda equals n, right? Where n is just the counting numbers, 1, 2, 3, da 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 da. All right. Okay. So if lambda's n, just the integers, then so we've got a value for lambda, and hence we can find the energy eigenvalues, because we've done this several times before. But lambda is a whole bunch of, what is lambda? I never remember. Lambda is a whole bunch of constants within the denominator and alpha. And alpha squared has the E value, the energy, in the numerator. So if you know lambda, you know alpha, and if you know alpha, you know E. Okay, so indirectly, if you know lambda, you know E. Okay, we know lambda. It's just the integers, positive integers, and therefore we can find E. Solve for that. You plug. So you can solve for E, and you get this expression. Then